Hello, everybody, and welcome to the second class on probability and combinatorics. And we are today going to talk about some of the basic principles of counting, which is called permutations and combinations. And then we are going to apply those principles to some problems that involve both probability and also combinatorics. So combinatorics is this field of studying combinations. It's a very important field in computer science and also in math. It comes under discrete math, so it's one of my favorite areas. In a day-to-day situation, when we live a normal life, it is very, very normal for the human mind to always think about different combinations. We use the word combinations in a very general sense. Actually, there are two different words. One is permutations and the other is combinations, and I will define those terms soon. But for now, let us stick with the English definition of combinations, right? So when we say combinations, we say in how many different ways can something happen? So we say, hey, I want to wear this clothes. I want to wear this dress today. Should I wear a red shirt and a blue pant, or should I wear the red shirt and the black pant, or should I try it with this hat? So we try to do a different, we do different combinations with our clothes. For example, now recently that I've been starting to live alone, I have to cook a little bit, and I see what sort of dish can I make. So should I combine this vegetable and that vegetable, or should I combine that recipe with this one? So it gives variety to life. So sometimes things can get boring if we don't try different combinations. And one of the most interesting ways of thinking about combinations, for example, let's say a game of chess, which is arguably the most logical and famous game in the world. We say, in how many different ways can a chess game happen? Meaning there are different ways, right? You can have different opening. You could have a different strategy where somebody plays out with the castle, or somebody plays without a castle. You could have a strategy where somebody plays with primarily with their bishops, or you could have it with the horse or whatever. So it can change. So there are many different ways. I think the actual count is more than 2 billion. There are more than 2 billion legitimate chess games which are possible. And you are not allowed to go back on your move, because then you can have infinitely many games, right? I could just move my knight and move it back, move it again, move it back. So the two people can keep doing that, but that's not the way. So you cannot backtrack on any moves, and you just keep playing. There are 2 billion plus ways, and that is why I think the game is continuing to have such a popular influence even today, because even in so many years, because there are 2 billion different ways a game can be played, no human being in his life will play more than, I don't know how many. Even let's say you play a game every day of your life, so 365, and you live for 100 years, you'll play only about 36,000 games. So that's not a lot, and there are 2 billion games possible, which means that things can always get interesting. That's why so many people can play it so many different times, and every game is having a new feel to it. Although when experts play together, they have probably 1,000 games which they will switch between, but in reality there are a lot of possibilities. The other thing is, if there are many seats and people have to sit on them. For example, when we were young, I don't know if the things happen now in schools, but when I was in, let's say, 5th or 6th grade, we were assigned seats every month. And the teacher would make us all stand in a line, and we would be made to sit. And the teacher would be very careful not to make me sit with my friend, because I would talk a lot, or they would make sure the tall people sit at the back, the short people sit at the front. Then they would keep a row of girls, and then a bench of girls, and then a bench of boys, and etc. So there are different things that there were rules, there were different criterion. It's not randomized. So then you say, in how many different ways can the people be seated? Because every 2 weeks or every 3 weeks, I think the places were changed. And throughout the year, we should never have the same place again, because then people will complain, no, I sat with this guy for 1 month, I want to change to somebody else, or I want to sit near the window, I don't want to sit next to the wall. So things can happen, right? So that is how, on a day-to-day basis, we think about combinations, and we think about ways of doing things in a different sort of way. One interesting thing that I want to tell you about, which you should think about actually, is something called de-arrangement. It's a concept that I was recently introduced to. We all know what is arrangement. Like, for example, let's say there are 10 chairs and 10 people, and they're sitting in some way. De-arrangement is a way in which you change their places such that nobody is sitting where they were sitting earlier. Okay. And then the question is, how many ways can that be done? So I will leave that to you to think about, so that we can discuss that in the next class. Or let's say you go to a restaurant and there are 15 people and each person orders a different flavored juice. Okay, no one orders the same thing, 15 different flavors of juice, and the waiter doesn't know who ordered what. Apparently he's a new guy and he just randomly distributes the drinks. What is the probability that nobody gets the drink that they ordered? So that is again the concept of dearrangement, and we will focus on this next time. I'm just giving you some examples from the top of my head as to where we will use combinations and probability on a day-to-day basis, right? It's not just, so the thing about this sort of branch of mathematics is called applied math, and it also comes under theoretical computer science. So these things are seen more often on a day-to-day basis, as opposed to, let's say, number theory or calculus or abstract algebra. These are sort of things that you would only go into if you are actually a mathematician or working somewhere as an engineer, or you had to apply a lot of you are studying some aerodynamics and things like that. You would probably use trigonometry and calculus on a day-to-day basis. But probability and permutations and combinations are used in almost every field, like the entire field of machine learning, data science. All these things are completely based on these theoretical aspects of computer science, which come under discrete math. Okay, so now before we dive into some interesting problems, I think I have 5 interesting problems that we will try to solve all today. I don't know if we have the time for that, but we will try our best. The first thing I want to talk about is the actual definition of permutations and the actual definition of combinations. Now suppose I have 10 people and they have to stand on a line, they have to stand on a straight line. In how many different ways can I make them stand? This is a simple question, and I think most of us know this. And my clue, the clue that I will give you is an exclamation symbol. It's a very simple clue that I'm giving. It's exclamation symbol is the clue. Okay, somebody has sent me the answer. That's correct. I want to see if somebody else knows that too. Very good, very good, very good. Somebody has actually sent the number, which is interesting. Okay, yes, so the answer is 10 factorial. And factorial is just multiplying every number smaller than you all the way up to 1. Okay, you don't multiply by 0 because then every factorial would be 0. And the interesting thing is 0 factorial is also considered to be 1, and we can get into discussions about that later, because if you're multiplying by everything, then what are you actually multiplying by, right, to get 1 if the number itself is 0? Similar argument to 0 to the power 0 also being 1. So we will focus on those things maybe on some day when I'm extremely free and all of us are just chatting about math in general. We'll talk about why negative times negative is positive, why 0 to the 0 is 1, and all those things. As of now, let us just talk about factorial. So 5 factorial would be 5 times 4 times 3 times 2 times 1, which is 120. Okay, so if there are 5 people, we can arrange them in 120 different ways. And now this is the basic counting principle. We don't need to know any formula here. We just have to understand the logic. Why is it factorial? Because assume that the 5 people are standing in 5 different positions, right? There's the first position, the second, the third, the fourth, the fifth. The first position can be taken by 5 different people. You can have 5 different people stand over there, right? Each time you can have somebody. The next position can have only 4 different people because one person is already standing here. We don't care who the person is, but somebody standing there. So then there are 4, then 3, then 2, then 1. So the last position can only be taken by one guy because 4 people are already taking those other 4 positions. So the different ways that can be done is 5 times 4 times 3 times 2 times 1. You could do the same thing reverse. You can start from the other side. You can still say 5 times 4 times 3 times 2 times 1. But multiplication is commutative and associative, so we don't really need to think about that. So by the way, before we talk about the combinatorics problems, I have one question for you, which is a very basic question, but I want all of us to think about it because it's sometimes important to get that cleared. Why is multiplication actually commutative? I'm not going to ask you why addition is commutative, because I think that's too trivial. But why is multiplication commutative? Because division is not commutative, subtraction is not commutative. Why is A times B the same as B times A? We don't need to prove this with a lot of rigor. We'll just try to come up with a simple example to understand why this is so. Okay. Why is 5 times 6 equals to 6 times 5? Okay, let's say we know the answer, like 5 times 6 is 30. We say that 6 times 5 is also 30. But what if you're talking about two really big numbers, something like 1,000,000 and something else? How are we so sure that even if we change the order, the product will remain the same? And, once it is shown like that, then we can say that it's associative. If there are even 100 different things, we can multiply them in any different order, the answer will be the same. Why is it so? We are told in 5th grade that it's true, but does anybody have a proper explanation as to why multiplication is commutative? Can somebody say with conviction why it is so? Okay, so Shreyan, do you want to say? I will just unmute you for a second. Can you raise your hand? Let's just discuss about this. Okay, so yeah.
Yeah, the way we generate natural numbers or, and integers is that
Yes.
first I'm going to prove that I'm first going to prove commutativity in natural numbers.
Uh-huh.
Then I'm going to prove it in higher fields. Okay.
Shreyan, hold on. Just don't worry about the higher fields. Just tell me why in natural numbers A times B is B times A.
Okay. So we know that in natural numbers, we represent the next natural number as the set as a function of the earlier natural number.
Okay.
Okay. The
Yes.
exact function requires you representing natural numbers as something else.
Yes.
But it has some properties that it never loops and it never.
Yes. There's
And no
cancellation
to no.
property. Yes.
Yeah. So we have to. So it depends on the number of times we apply it.
Okay.
Okay. So if we multiply a number x by number y, we have first applied this function x times, then we have applied this function x times, then we have applied this function x times, and so on. Y times.
Yes.
Okay.
Yes.
We have not multiplied. We have put this function.
Yes.
So then what happens if we take one function from each of those groups, then the second of those functions from each of those groups, and third functions, we can rearrange it into saying y. We have taken y, and because there's x in each of these groups,
You have taken
we
y
have
x times. Yes.
yes.
Yes. Okay.
So we have x groups of y,
Yes.
which is y times x.
Thank you so much. Okay, so what he said is perfectly correct, and he spoke in a very wonderful way, because he was actually talking about the construction of natural numbers, which is a something that is taught later on, only when you go into some higher level of mathematics. An easier way to understand it would be applying the simple formula of the area of a rectangle, right? That's how I explained this to one of my students who is in 3rd grade. So what we know is that if there are people standing in a rectangle, we want to count the number of people. We will say that we will first count the number of people standing in one column, and then we will multiply the number of columns, right? So let's say the column is x and the row is y. We'll multiply number of columns, so the number of people is the same. And now we will say the same number of people are standing in the same position, but we will count them horizontally. That's, we count each how many people are there in each row, and then we multiply that by the number of columns, by the number of rows, I meant. So the people have not changed. The answer has not changed, because the answer is to count the number of people. But we first counted but the first we did it was by counting the number of people in a column and multiplying the number of columns. The second time what we did was multiplied the people in the row and multiplied by the row. So actually we are just doing the same thing, x times y and y times x, but it's commutative, so the answer is the same thing. So that's like a trivial way to understand, but in reality what Shreyan said is correct. That's how the natural numbers are constructed. The way multiplication is defined is that it is repeated addition, and addition is commutative, so repeated addition is also commutative. And when you apply the function y times to x, it's the same as applying it x times to y. Okay, so now let me share my screen, just a second, and we will talk about. Okay, so this problem has been discussed, and I will not talk about this now. By the way, I just want to ask you, have I discussed the answer to the birthday puzzle where there were 3 kids and the product of their ages was 36 and the sum of their ages was today's date? Did I actually give you the answer to that puzzle, or did I just give you the puzzle? If I've not given you the answer, then I will give it at the end of the class. Okay. So now that we spoke about the factorial, there's one more thing that I want to tell you. Just a second. Let's write those things. I don't know why this is showing number 7. Anyway, so it's continuing from the previous class. So the first thing is number of arrangements is n factorial. We discussed about that. Now combinations. Let's say now I want to talk about how many ways can I choose 2 objects from n objects, right? Or how many ways can I choose 5 objects from 35 objects? How do you explain that, right? I want to pick 5 things. For example, there's a class which has 39 people, and I want to choose 3 people who will represent the class in a math Olympiad, but I want to pick them randomly because everyone is good. In how many ways can I do it? How many ways can I pick 3 people from 39 people? So the formula for that is n factorial, where n is the number of objects, divided by p factorial, where p is the number of people that we want to pick, times n minus p the whole factorial. Now this whole thing is inside a bracket, so it's in the denominator of the fraction. So let me write it in a better way for you to understand. So it's actually n factorial. I don't know why this is capital. Anyway, n factorial divided by p factorial multiplied by, let me write x, n factorial divided by n minus p factorial. So the example with the class 39 students and 3 students is the number of ways by which we can choose those 3 people from those 39 people is 39 factorial divided by, actually let me put okay, fine, divided by 3 factorial multiplied by 36 factorial, because 36 is 39 minus 3. The oh sorry, just a second, this is 1 by, not n factor. This is 1 by, because both of them are in the denominator. I just want to let you know. See, when we talk about combinations, I just want to clarify one thing. Now I say I want to pick 3 people from the class. Let's say the 3 people, let's say their names are Janet, George, and Colin. The people from Secret 7 or Famous 5, whatever, I don't know. Janet, George, and Colin. Now combinations tells me that Janet, George, Colin is the same as Colin, Janet, George is the same as George, Colin, Janet, because I'm talking about which are the 3 people that I want to pick. I'm not actually discussing about in which order they're being picked. I just want 3 people out of 39 people. So if those 3 people are Janet, George, and Colin, they are the 3 people. It doesn't matter if I chose George first or Janet first, but these are the 3 people. If we want the order of our choices, then it's permutations. Okay. In permutations, what happens is we are actually bothered about the different order in which it's picked. For example, Janet, George, Colin will be different from Janet, Colin, George. So they might be the same 3 people, but because I actually care about the order. So I'll tell you how this matters. Let's say that there's a competition, there's a running race that happens in the class, right? There are 39 people, the same class of 39 people. There's a running race that happens, and I want to see how many different results are possible. It's not representing for a math Olympiad, because when I say representing for a math Olympiad, then it is actually just going to be combinations because I want to choose 3 people. But if I actually say it's a running race and the result matters, then it matters who is first, who is second, who is third. So that formula is quite similar, nothing different. It's just n factorial divided by p factorial. I'm not worried about this n minus p factorial. I'm not going to be dividing it by that again. So you can understand that this is going to be a lot larger. I hope all of us know that fractions, if the denominators are smaller, the fractions are larger. If the denominators are larger, the fractions are smaller. So in the first case, the denominator is very large because we are multiplying p factorial and n minus p factorial. So there's a big denominator there, which means we can say the fraction as a whole will be pretty small as compared to the second one, because here the denominator is very small. So for the 39 students problem, the permutations would be 39 factorial divided by 3 factorial, which is so big because 39 factorial is humongous. 3 factorial is so small. But in the combinations case, it is not so big because it's 39 factorial divided by 3 factorial times 36 factorial. So if we actually calculate this out, we don't have to actually calculate 39 factorial because we can cancel it with the 36 factorial. See, the 39 factorial is of the form 38, 37, 36, blah, 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 all the way up to 1. But we are dividing it by 36 factorial in the denominator, right? So we can just get rid of all of this. It's gone. So we just are left with 39 times 38 times 37 divided by 3 factorial, which is just 6. So this number is relatively smaller. It's going to be how much? 40 times 40 times 40 is going to be close to 64,000, right? No, it's going to be more than that. 40 times 40 times 40 is, yeah, 64,000. Yeah, not too much. So 64,000 divided by 6, we can just roughly say this is going to be somewhere close to 11,000 for combinations. But when you do permutations, this is going to be 39 factorial divided by 3 factorial. And I cannot even calculate that number here. 39 factorial is too big. Dividing by 3 factorial will not make it much smaller because we are going to multiply all the numbers from 39 all the way up to 4. So permutations are always more. Combinations are sometimes more important to us in our problems because we don't really care about the, see, for example, if we have 10 different, what do you say, 10 different shirts and I want to pick 2 of them, I just care about the combinations. I don't really care about the permutations, because if I have a red shirt and a blue shirt and I'm picking the 2 of them, the red and the blue is not different to me from the blue and the red, because I'm technically just wanting to pick 2 shirts. I don't really care which shirt I picked first or which shirt I picked second. Oh, sorry. My bad. Just a second. Hold on. This, I made a mistake here. Just a second. Sorry about that. This didn't look correct. This was too big a number. Yeah. It's not n factorial divided by p factorial. It's n factorial divided by n minus p factorial. Sorry about that. I was just thinking, how can we have a class of 39 people where the number of results possible is something like 39 factorial divided by 6? That just didn't make sense. Okay. So this is still going to be larger than the combinations, but it's not going to be that much larger. This is just going to be 39 times 38 times 37. Yeah, sincere apologies, guys. Just a second. Let me correct this properly. We have to divide it by n minus p factorial, not by p factorial. P is so small compared to n factorial that just didn't look right, but I didn't think too much about it. So in this case, the permutations is going to still be close to 64,000, but the combinations were something like 10,000 as we roughly estimated it. So this is still more because we are worried about the order. So now we can intuitively understand why this is this formula when compared to this one. So let me tell you why. Let's think we have the formula for combinations as n factorial divided by p factorial times n minus p factorial. Now we have the combinations. We want to find out how many ways are there to pick those people, but the order matters. What is the order according to the first thing that we did? If there are 5 people, how many ways can we arrange them? in 5 factorial ways. So what we are actually doing is we are just multiplying this combinations formula by p factorial. Why p factorial? Because in each of our choices, there are p people, right? So just combine the two problems. The first problem was to say we want 3 people to represent the class in an Olympiad. Now we want to say what are the results possible in the running race. Now the people who we picked for the Olympiad, we can have the same sample set because now we have distributed the whole class into different possible groups of 3. But now we want to multiply each of those by 6, because in each of those groups of 3, we can have the first guy come first, the second guy come first, the third guy come first, and then the other 2 changes. Like for example, let's say here we picked a team of Janet, George, and Colin. For the Olympiad, we don't care about the order. But now when we talk about the running race, for the same combination, the order matters. So let me say they are J, G, and C. We can have right? We can have 6 different ways of arranging them. For the same 3 people, we pick 3 people out of the class of 39, and for them we can arrange in 6 different ways. This could be done for every single group of 3 that we picked. So we are multiplying this whole thing by 6, because in each of those combinations we can arrange them. Okay, so that is the main what do you say, moral of the story of permutations and combinations. And I hope you will remember this formula at least for today when we look at some of the problems. They're not too hard, but we will have to apply a little bit of logic to some of them. So now let us go to the first problem. I don't know why this is numbered 7. I think because it's continuing from the 6th problem of the last class. Okay, this is the first one, and this actually I want to give you a clue. This doesn't actually involve too much of any of these formulas, but you have to think a little bit. But let's see. A bag has 6 white socks and 7 black socks. What is the least number of, why did I say balls? Let's say socks. Some of the problems are, okay. What is the least number of socks that have to be drawn from the bag to be assured of having a pair? A pair is 2 socks of the same color. Now the question is, there are 6 white socks and 7 black socks in this bag. So first thing we want to know is how many are actually there in the bag, which is 13. Okay, there are 13 socks in the whole bag and there are 6 white and 7 black. We want to see what is the least number that we have to pick so that we will have 2 socks of the same color. Can you all think about it and type an answer to me privately, and then I will tell you why it is so. I am waiting for somebody to type a wrong answer. Okay, somebody has typed a wrong answer. Good. Because everyone was typing the correct answer. I couldn't even explain the logic if everybody got it right. So I was just waiting for somebody. Very interesting. Okay, it's actually 3. This doesn't involve any combinations. It's just 3, because no matter what you pick, on your third try, you will be assured of having 2 of the same color. Because if your first 2 were the same color, you're already done. You have a pair. If both of them were black or both of them were white, if let's say the first was white and the second was black, or whatever, the first was black and second was white, no matter what you pick on your third attempt, it will be at least black or white. So you will have a pair. So this is not actually a combinations problem. It is just to make you think, a little bit and get you started. Okay, now this is a combinations problem with a little bit of probability. So remember, what is probability doing and what is combinations doing, and we are combining both of those things. Probability is telling us what is the chance of an event happening. Combinations is telling us in how many different ways that event can happen. So the first thing we have to do is calculate the different events possible, and then we have to say what is the chance that the event that we want happens. A bag has 8 white socks and 6 black socks. What is the probability that a pair is drawn if 2 are picked? This is not a silly problem. I want all of you to actually think about this and think about the problems. Let me just write down these formulas again, because I actually confused you a little bit probably. So let me just write it here. Okay, so there are 8 white socks and 6 black socks. And what is the probability that a pair is drawn if 2 are picked? So we just pick 2 socks at random from the bag, and we want to see what is the chance that we have a pair. We don't care which pair, but it could be black, it could be white, but we just want to see what is the probability that it is a pair. I'll allow you all to think about it. And this is not a trivial problem, but I think we can understand how actually these concepts work when we understand how to solve this problem. Just think why this formula is required for this and try to see. I'll give you a clue to get you started. Okay, I'll give you a clue to just get you started. Before thinking about the pair, just think about how many different ways can two socks be picked from this entire bag. So what is the definition of picking, choosing? It's combinations, right? So we want to see how many different ways can I pick two socks from 14 socks. How many ways can I pick one sock from 14 socks? 14. Because there are 14 socks, I can pick one sock in 14 different ways. And if we apply this formula here, it's actually going to be 14 factorial divided by 1 factorial multiplied by 13 factorial. So it's technically 14 factorial divided by 13 factorial, which is just 14. I apply the same formula for 2. You don't have to actually write down the answer completely. You can just leave it as, so we actually, the way we write combinations is we write it as, suppose I was choosing 3 people from 39, we write it as 39C3. Or if I'm choosing 2 from 14, I write it as 14C2. This C stands for combinations. If it's permutations, I would have written it as 39P3, or I would have written it as 14P2. But we don't care about permutations now, we're just worried about combinations for this particular problem. So 39 choose 3 means 39 factorial divided by 3 factorial times 36 factorial. So that is the, it's understood if you write 39C3 that you're talking about combinations. It's always interesting to think about where we require the combinations formula and where we require the permutations formula. So you have to think about the situation. In this case, we are talking about how many ways can two socks be picked. It doesn't really matter about, it doesn't really, we don't care about the order, because now there are 8 socks. I want to pick 2 from that, let's say, or if there are 14 socks, I want to pick 2. It doesn't matter if I'm having 2 white socks and the first one is a white and the second one is a white. I mean, it's the same thing, right? How do you differentiate between 2 white socks? So the order doesn't matter. It's just the quantity that's in focus here. So the total ways in which socks can be picked from the bag is 14C2. Is everybody in agreement with this particular thing? We have 14 socks, out of that we have to pick 2. So it's 14 choose 2, which would be 14 factorial divided by 2 factorial times 12 factorial. If you are confused about this, just write down in the box. But if you're okay with it, just don't have to. So if somebody didn't understand the notation, okay. We are talking about combinations here, and this is the way to calculate combination. That is, we want to see in how many different ways. Here P stands for the number of things that we want to pick from, number of things that we want to pick, and N stands for the total number of things. So in the class problem, the total number of students was 39, so N was 39. We wanted to pick 3 people for the competition, so the P was 3. P is pick. Think about P stands for pick. How many people we want to pick? How many socks we want to pick? P. N stands for the total number. N is number. So the way to calculate combinations is you divide N factorial by P factorial times N minus P factorial. Okay. So the way we could calculate it for this particular problem is there are 14 different socks and we want to pick 2 out of that. So the total ways of doing it will be 14 factorial divided by 2 factorial times 12 factorial. 12 is 14 minus 2. So let me actually write down the formula. Since this is the first problem that we are doing properly with the formula, let me first write down the formula. This is N factorial divided by P factorial times N minus P factorial. This is the formula. Okay, so in this case it will be 14 factorial divided by 2 factorial times 14 minus 2 factorial. See, think about this intuitively. This formula would change if we want to pick 3. So then this would become 3 factorial divided by 14 minus 3 factorial. If we want to pick only 1, it would be 1 factorial times 13 factorial, right? So this is like a dynamic formula. It changes based on n, it changes based on p, but the logic is the same. We want to pick p things from total of n things. And the reason why we are dividing by this p factorial again is because we don't care about the order. If we actually cared about the order, we would just do 14 factorial divided by 12 factorial. But we actually don't want the order. We just want the choice because we're talking about combinations. That is this p factorial as well here. Because if you see for the permutations here, we just do n factorial divided by n minus p factorial. We don't multiply by the p factorial in the denominator because we don't want to, we actually want to count all the ordering again and again. So we just don't care about having 2 socks. We want to see which sock first, which sock second. So that's permutations. That's why the answer will always be larger because the denominator is smaller. But in combinations, we want the choice, not the order. So the denominator will be larger. Okay, so this is now going to be 14 times 13 divided by 2 because this 12 factorial can just be cancelled out with the 12 factorial in the numerator. This 14 factorial is just 14 times 13 times 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 6 times 2 times 1. We can just cancel that out. So this is going to be 91. Do you all agree that 14C2 will be 91? Don't worry about the problem. Just think about this 14C2. Think about this formula and see if the answer will be 91. Try to do it on your own. This is in the denominator. This whole thing is in the denominator. Now this is in the numerator. 14 times 13 divided by 2. I don't know if this looks like power. I can just put this, but that doesn't look right. So this star stands for multiplication, right? So we have 91. That is 14 choose 2. What exactly is 91? Thus, 2 socks can be picked from the bag in 91 different ways. Two socks can be picked in 91 different ways. If we label each of those socks to be first sock, second sock, whatever, 14 socks, we can pick 2 socks in 91 different ways. We are not talking about their color, meaning I'm not saying that there are 91 different colors that can be picked. There are only 2 colors. So technically speaking, it can only be white, white, black, white, black, black. But we're talking about the socks. There are 14 socks, 14 objects. And how many ways can we pick 2 objects from 14? It's 91 different ways. Now we want to look at the probability that a pair is drawn. So now we have the total number of events. There's a total number of ways of picking 2 things. Now we want to see how many ways we can pick the 2 things such that we want in such a way that we want it. Like for example, we want a pair. In how many ways can we pick a pair? Let us see. How many ways can we pick a pair of white socks? That is 8C2. Because there are 8 white socks, we want to pick 2 white socks from that. We can pick them in 8C2 ways. We can pick 2 socks from 8 socks in 8C2 ways. How many of you did not understand this? Just type something in the chat box. We are done discussing about the number of ways we can pick 2 from 14. Now we are talking about how many ways we can pick 2 from 8. How many ways can we pick 2 socks from 8 socks? 8 choose 2. So that's going to be 8 factorial divided by 2 factorial times 8 minus 2 factorial, which is now going to be 8 factorial divided by 2 factorial times 6 factorial, which is going to be 8 times 7 by 2, which is 28. Same logic as this one. Exactly the same calculations. We are now just listing. Before we do the probability, see what is the formula for probability? What was the thing that we discussed last class? probability is favorable events. Okay, this is American spelling. Okay, favorable events divided by total events. This is all that is, right? Probability is talking about what we want divided by what everything is. So we first calculated what everything is. That is 91 different ways we can pick two things from 14. But now we want to talk about how many pairs are possible. So there are 28 ways in which a white pair can occur. Now let's do the same thing for the black sock. So there are 6C2 ways of picking them. That's going to be 6 factorial divided by 2 factorial multiplied by 4 factorial. I think all of us can quickly, we can skip this step. 8 minus 2, 6 minus 2. This is going to be 6 multiplied by 5 divided by 2, which is 15. Is everybody understanding what's going on? I'm now calculating how many ways we can pick 2 socks from 8, then 2 socks from 6. So there are 28 different ways of having a white pair. There are 15 different ways of having a black pair. So it's intuitively also making sense, right? There are only 6 black socks, so the number of pairs will be smaller. There are 8 white socks, so the number of pairs will be larger. Thus, the probability of picking a pair equals 28 plus 15 divided by 91, which is 43 divided by 91. I'm going to pause for 2 minutes now, just allowing all of you to just read over this, whatever has just been written. It's a lot of things, I know. In fact, this is probably a slightly complicated way to start thinking about combinations in general. But I think this talks about all the concepts that are required. So even if we take some time to go over this, it's fine, because it talks about probability, it talks about counting, it talks about this combinations formula, and it talks about favorable events. So I think it's a good idea to go over this problem properly. Somebody has just messaged me an alternate way of doing this problem, and I will tell you what that is. But this is a good exercise to understand how combinations actually works. So let's see. We first checked how many ways 2 things can be picked from 14. Then we checked how many ways 2 can be picked from 8 and 2 can be picked from 6. And then we just put it in the numerator and the denominator. See, I'll tell you how to make full sense of this situation, right? Instead of just thinking about it in terms of formula, I'll tell you how to think about it in a proper situation. Let's say we have many different friends who are all called to our house for this particular experiment, okay? We will say that we have hundreds of friends. We don't care how many friends we have, but we have a lot of friends. And to each friend, we will give this bag, which has 8 white socks and 6 black socks. To each friend, the same bag with the same number of socks. Everybody gets a duplicate copy of the bag. And now we tell each of them to pick 2 from the bag. But let's say these people are computer programmed and no 2 of the friends will do the same. Nobody will pick the same 2 socks. Like, people will pick 2 different things, but in a different way. Like, both of them might pick 2 white socks, but this guy would have probably picked the first and the second sock, but that guy would have picked the third and the fourth sock. Let us just artificially create such a situation where nobody picks the same thing. So then we will have 91 different picks of the same bag. We'll have 91 friends who will each pick a different thing. One guy will pick the first white sock and the second white sock. Somebody else would probably pick the eighth white sock and the third black sock, or whatever that is. And now we will see, out of those 91 people, how many of them would actually have 2 white socks and how many of them would actually have 2 black socks. And we'll just add it. So that will be 28 plus 15. 43 of them will pick a pair. Exactly. If we apply too much of reality into it, then it might not actually be easy to think about it, because everybody might end up picking the exact same 2 white socks and everybody might have a pair, because this is probability. The chance of that happening is also there, but we are assuming that each person picks a different thing. Okay, now the different way to solve this problem is by applying the other formula of probability, which I told you in the last class. I don't know how many of you remember. Probability of something happening equals 1 minus probability of something not happening. So the total probability is always going to be 1, right? No matter how many events you have, whatever is your chance, the total is going to be 1. So if we want to calculate what is the chance of something happening, we can first calculate what is the chance of that not happening, and then we can take the complement. It's like we have two angles and we know that both of them add up to 90 degrees, and we know that one of them is 57, the other one has to be 33. So it's like complementary angles. If say India has 47% chance of winning a match, we can say that they have 53% chance of losing the match or not winning the match, right? You remember that example that we discussed last time? So what we could calculate here, this requires a little bit of thinking, because you should first understand that we have to apply this logic, is we could see what is the chance of not getting a pair. What is the chance of not getting a pair? And then we can subtract it from the total possibility. So the first step is the same. We have to calculate 14, choose 2. And now we say, what is the chance of not having a pair? Well, to not have a pair, then one should be black and one should be white. They cannot be the same thing. And how many different ways can you pick that? 48, because you have 8 white socks and 6 black socks. So the total ways in which you can pick the two of them such that they are not the same is going to be 48. That's counting principle, right? The same thing that we talked about in the beginning of this class, talking about factorial, talking about how many shirts we have. If we have 3 shirts and 10 pants, the different combinations will be 3 times 10, right? So not picking a pair is 8 times 6, which is 48. So the chance of not picking a pair would be 48 over 91. So chance of picking a pair is 43 over 91. Because it's just the total ways of picking 2 socks from that bag of our good old bag of 14 socks is 91. You can pick 2 different things in 91 ways. So if 48 ways are not going to work for you, then the other 43 have to work for you. So the the interesting thing that we can check now, I don't know the answer to this one, but I want to check this and then we can stop for today. See, somebody just wrote that right now. This is 0.5% approx. So that's what I'm thinking too. This is almost the same. The chance of having the pair and not having the pair is close. Could it exactly be the same if I have 7 black socks and 7 white socks? Would it be the same? Let us just check. Because I'm thinking the chance of not having a pair is a little higher. Could that be because there are 8 white socks and 6 black socks? So the black pairs are a little lower. Let's see. And the interesting thing about thinking about 7 is that it's not even an even number. So that makes it a little counterintuitive when we pick a pair. So let's just see what happens. So let's say there are 7 white socks and 7 black socks. The first thing that we want to check is this formula that we did, the combinations formula. The total ways of picking is going to still be 14 choose 2, because there are still exactly 14 socks. So we can pick them in 91 different ways. Well, this itself tells us that this cannot be 50-50 because 91 is an odd number, no matter what the chance. Let's just see what happens though, right? There might be a chance that something happens. Okay. What is the chance that we pick a black or a white pair? White pair is 7 choose 3, which is going to be 7 factorial, sorry, 2. 7 choose 2, which is going to be 7 factorial divided by 2 factorial times 5 factorial. 2 factorial, 5 factorial. This is now going to be 7 times 6 divided by 2, which is going to be 21. So 7C2 again for the black is also going to be 21. So there are 42. Now it's 42 by 91. Well. It reduced. Why? This is so counterintuitive if you think about it. We just have the same number of socks, but we have 7 white and 7 black. I thought if they're equal, that might make it a little bit more obvious that something will happen, but no. Well, actually, I didn't even have to do this because I know that the number of ways in which we don't have a pair is going to be 7 times 7, which is 49. So there's a lot more than 50% of 91. So we will think about this and we will discuss this next time. Why is it not 50%? Why is there a slightly higher chance of not having a pair? Why is there a higher chance of having a pair? Why is there a lower chance of having a pair? So we will talk about this next time, and